Brilliant.
All right, cool.
Okay, hopefully you guys can see my screen now.
We do, at least I do, and the audience as well.
Brilliant. Okay, well, thank you very much, Armin, for the introduction. And good morning, good afternoon to everyone that's attending the webinar. As Armin said, my name is Joyce, and I will be taking you through looking at the Design Explorer in HyperWorks, which is our CAE preprocessor. So within my demonstration, my speech today, I'll be taking you through looking at exactly what a DOE is. You'll then get a chance to watch a video to go through the Design Explorer demonstration. And then finally at the end, we'll address any questions and answers that you might have. So the Design Explorer tool, like Armin says, is packaged within our HyperWorks suite. And what you'll find is that if you have ever used HyperStudy before in the past, this is our design exploration tool. And the Design Explorer within HyperWorks is just an amalgamation between bringing in together HyperWorks and HyperStudy together. So before we do actually start, I just thought, I'd ask you guys a question. Have you ever conducted a DOE before? Do you know what a design exploration actually is? And this is the point where you might be thinking, I've probably never conducted a design of experiments before. I don't even know what design exploration is. Now, you might have actually been doing it subconsciously without even knowing throughout your whole time of your design process. So a DOE is basically looking at the sensitivities of design variables and your different input parameters. But you're probably thinking, what does this actually mean? What do you mean by sensitivities? What are we actually looking into? So say if we start off with looking at our original design, you'll see I have this design block here. And what's really good about it is that you probably know exactly how you want to set it up for an analysis. So you know exactly where it's being held, where your forces are acting upon it. So then you conduct your analysis and you say, your first run, your part has a thickness of 10 mil, it's using a steel material type, and you've received the stresses of 50 megapascals, and it displaces by 10 mil. In which, in this instance, you're probably thinking, I can probably reduce the thickness of it because my stresses are nowhere near my yield value. So you think, okay, if I halve the thickness, following our generic, F equals KU FEA equation, we might be thinking if we halve the thickness, we might actually get twice the stresses because we're looking to optimize our shape. We want to reduce the weight of it. So you conduct that and then you realize that within your second run, half the thickness doesn't actually give you twice the amount of stresses or twice the amount of displacements. So then from this point, you don't really understand your relationships between your input parameters and your output parameters as well. So your input parameters would be what it is within your design you're willing to vary, like your thickness or your material type, and your output responses would be the results that you care about. So at this point, when you don't really understand that relationship, you don't know how to go forward with your design. And you're just left with lots of puzzling question marks, and you really don't know how to take the next step forward. So this probably leaves you into this whole inductive loop where you've manually adjusted your deck again and again, and you still really you're not getting the right output responses you need. So what's great about the design exploration tool within HyperWorks is the fact that it's an automatic variation of your input parameters with respect to the output responses that you need. So if you have your original design, you're going to tell the software what it is that you're willing to vary. You're willing to change the thickness, you might want to change the size, you could change your morphed shapes, you could change certain parameters, and you can even change the material assigned to your part. You're telling the software what it is that you want it to change. The software will then automatically vary them for you. And you can also specify exactly what it is that you care about in terms of your results after you've changed these different variables. You might care about the weight of your part. You might care about how much a part displaces. You might want to make sure that your stresses in your part don't exceed the yield value, because once you've exceeded it, it's going to break. But these are all things that you can tell the software to care about. So then this automatic loop knows how to vary it automatically to achieve the performance that you need at the end of it. Now, we've kind of addressed it already, what input parameters it is that you can look into. You can look at the different dimensions of your parts. So it could be the size or the shape of the holes that you have. You can also then look at varying the materials assigned to each of the different parts. So currently it's using steel, but it could be that you might be better off using aluminium instead. But there's so many more other type of input parameters that you can use as well. For example, if you're looking at composites, you can completely change your laminate layup, the fiber direction, and your ply orientations. If you're looking at the way it's manufactured, you can change the surface finish, the extrusion direction, and so many more other parameters that you can vary. And then in terms of the output parameters, the things that you care about at the end, it could be your structural properties such as the mass, the stresses that go through your part, as well as your part's natural frequency, because we know we want to avoid resonance. We can also look at the manufacturing capabilities of it, so how much it's going to cost, the time it will take to actually manufacture your part. And there's many more other things that you could care about as well. So when we're talking about design exploration, a design of experiments, it's just a term to describe exactly, out of all of the possibilities of design choices that we could make, why is it that we've chosen the one that we need? And from that base point, what we're doing is we take our part we have and we call it the design space. So the design space is basically the area in which your part could take any sort of combination of different values, and you have all of the different versions that you could potentially work from. And that's what we call the design space. So it's anything that your design could be. What we then definitely need to do is actually narrow it down, because it's physically not possible to try and manufacture every single different combination of designs that you have, or even to simulate them. So what we have is a design space. We're going to narrow it down due to the constraints and certain performance targets that you need it to reach. Once you've narrowed it down, you then want to actually sample a variety of how your part would perform throughout all of the design space. And with that data that you have, you can then find the trade-offs and understand the sensitivity of your parameters. So it could be that if you wanted to decrease the stresses in a part, increasing the length of one part of your dimension of your part could be better than trying to change the height of something. And that's where we find all of the relationships between them. And once we start from, let's say, your first design iteration, we change it once, and we actually have a general direction. And through this general direction, where we start meeting all of the performance targets that we need, where it's become even better than our first design, and that's where we'll realize that out of this sampling space, you'll be able to find your optimal design. And that's basically what we call design optimization using DOE in a nutshell. So when you open up the HyperWorks software, you'll see that you have a Design Explorer tool. And within the Design Exploration, you'll see in the demo later where you can bring up a browser. And when you do have your results, you can load your results up. It will show you your optimal design, and you know exactly where you can work from. So within the Design Explorer tool, it gives you your design sensitivity studies. So it allows you to fully comprehend your designs in that if you were to vary one parameter, how does it affect your results? It does both a DOE and an optimization. So like we said, it's basically HyperStudy being brought into this software. So it could be called as a mini HyperStudy. So if you've done your HyperStudy, this Design Explorer tool, Design Exploration study in HyperWorks, if you did want to take it further and conduct even more data mining studies with it as well, such as a stochastic study, you can actually take this file out of HyperWorks and open it in HyperStudy 2. You have an end-to-end workflow, so everything can be done in one GUI. From where you bring your CAD in, you mesh it up, you set it up for an analysis, you can then take it straight through into a DOE. And last but not least, it is really easy to use. You get immediate insight into it, and I know for sure that if I can use it, all of you guys can use it too. So at this point, I'm going to ask Jan to play the video, of a demonstration that I've done earlier in time. And this is a video that you can also access in the future if you want to conduct the same tutorial on your side. Okay, so within this video, I'm going to be showing you exactly how you can use the Design Explorer tool within the new HyperWorks 2021. Now, by the end of this video, hopefully you'll also be in a position where you can take this bike frame after you've conducted a design exploration on it, a DOE. You can start looking at whether if your input responses have a linear effect to your output responses, so you can see whether if your displacements are positively or negatively correlating towards your input variables, and if they are, then how big is the effect on all of the different responses that you have. So we're going to go through and show you exactly how it is you can post-process this. We're going to show you how you can take the data that you do have, that you've accumulated from all your different runs, where you can conduct a fit, and you can see whether if you were to interpolate it for a value which you didn't solve for, how accurate these output responses can be estimated for you. Obviously you can also put down a different scatter plot. We can go back to our different runs that we've conducted, so altogether we have 40 sets of data that we can look at, and how you can simply right click, load some results, and you can see exactly within this run where we've got all of these different thicknesses that we've input into this bike frame, we can see exactly how it's performing. And you'll see that the Design Exploration tool will automatically extract the output responses that you care about. So without further ado, let's actually start looking at conducting this ourselves. Okay, so let's start a new session of HyperWorks, and what I'm going to do is bring in my original bike frame model with it too. So here's a new session of HyperWorks. You can see that we're currently in the geometry toolbar, we're working in the model browser, and this window here would be where we do all of our modeling entities. So that would be the GUI where we interact with the model. Now if I were to bring up folder, here I have my original model. I can simply drag and drop it in to open it up, and you can see I have a bike frame here. We have a few components of different tubes. You can see it's loaded in the one load case called crank, and with this we can see exactly where all of our constraints are attached to our model, and we can also see that we have a force acting at the center of this crank. So what we're going to do is first just look at the model that we're dealing with. We can see that we have quite a few different property cards, so each of them have a different thickness. Well, currently they're all the same at 2 mil. And what we can do is, just to add to our design exploration a bit, what I'm going to do is morph this location of this part and see if the location of this part will have any effect on our final results. So if you head into the morph ribbon and click on free morph, we're going to move faces, and I'm going to move this part here. And what we're going to do is just click on this plane. Let's say we add 50 in the x-axis, and let's extend the height of it in Z by 100. And if we're okay with that, simply right click and swipe left to exit out of the tool, and you can see it's now morphed itself properly. So if we go into the shapes, there's a plus icon. What I'm going to do is click on the plus, and I'm going to add it as a shape. So how we go about this is the fact that I can rename this and call it height, and what this does is that if I undo all of my morphing, so I'm back to the nominal position that I was in previously, I can then preview all of the other sort of morphing variations that I have within this model. So if I were to click on preview, you can see exactly how I'd move it by and how the rest of my components would adjust and morph itself to the new design. I can do the same with this taller morph as well. It just extends the height of this blue tube, and the same with the crank radius. I can extend this one, and you can see the moment we preview it, it increases the size of that hole. And with the morph volumes, you can see that they're represented with different vectors. So all these node perturbations will change the position of those nodes. So now that we have a few variations in our design, what we want to do is actually see how changing that position of this part and changing the size of this radius, and maybe even changing some thicknesses in the bike frame would affect our results. So to start with, what we need to do is actually understand how it's currently performing. I ran an analysis on this bike frame already, so we know that if I wanted to look at the stresses in our subcase crank, what we can do is look at where our maximum stresses occur, and we can see they're mostly around in this component here, as well as this one there. If we want to then check for displacements, we can see that it's fairly minimal, around 0.08 being in this component, but then if I were to look at all of them, and it's still roughly, it moves the most at the top of this bike frame. So now that we have a good understanding of how our bike's performing, we can obviously conduct a DOE to understand how it is we want to improve its performance. So back to where we were, in this case, we're going to head into the Design Explorer toolbar. Within the Design Explorer toolbar, you'll see that we have the ribbon to access how it is that we can conduct a DOE. We'll click on this plus sign, and within this plus sign here, we can then add a DOE. And with this newly added DOE, we can also specify exactly where it is we want to save it. So one of the things that I just wanted to make you aware of is that when you do conduct a DOE, just make sure you have enough hard disk space, some hardware space to put it all in. So in my delete me folder, what I'm going to do is create a new folder, and I'm going to name this demo. I want to save all of my results into this demo folder, and you'll see that the location is all located here for me. Once that's done, if you were to click on this compass, because we want to find the direction in our designs, you can see that this brings up our Design Explorer browser. And it's great because then from this point here we can go through and click through exactly what inputs we want to put in and what outputs we want to get out. So let's start with looking at gauge. Gauge basically looks at the thicknesses of your properties. I want to specify a DOE to explore the thickness of this part, this part, this part, this part, and let's do this one down here as well. We can give it a percentage by how much it can increase and decrease by. So let's say I want to increase it by 100, and we can also decrease it by 50%. So it can either double itself in thickness, or it can reduce itself down to being half its thickness. And just so you know, you have other sort of settings that you can implement. So you could have it so that they're discrete values if you want to increase or decrease in that format, or you can increase it or decrease it in the form of a percentage. I'll just keep mine to percentage, and the moment you click create, you'll see all of your input variables are created for you. Now at this point, I can then go through and specify that I also want to incorporate my morphing techniques into this. I only want to focus on my crank radius and the height of my bike. Click OK, and they're also there for you. But just so you know, you can look at the dimensioning of your different beams. You can also look at changing the material card assigned to your different properties to see whether if maybe aluminium or steel would be more appropriate to the design that you have. Now at this point you can see that if I were to click on any of these tiny tables, I can look at the review inputs. You can see that we're playing around with the thicknesses of our components, and we have two morph volumes. In the details, this is where you might want to change some specifications. So where it's 0, it might be something that you can change. So let's just say for now that I'm willing to let these thicknesses go down to 0.5. And what I can do is just assign 0.5 to all of them, because obviously if our property thickness goes down to 0, we're going to get errors, as with 0 property thickness means 0 stiffness, 0 mass, so it's not going to work. But we can move it down to 0.5 for now. And what's nice is that within the same input table, if I were to click preview, so if I didn't know what the seat tube thickness was, I can click on preview. It will show you in isolation that we can look at this, and with the preview slider here you can see what it looks like when it's at its absolute thinnest, and what it looks like when it's at its absolute thickest as well. So this preview shows you exactly what it is that it will be varying. I can also click on height, and it shows you that it varies the positioning of these three components. Same when I do it with the crank radius as well. You can also create links between your different thicknesses. So say if you know that certain tubes have to be the same thickness as another one, you can always link them up so that if one of them's one thickness, the other one follows with it. So that's one way you can review your inputs. Now on the next part, what we can do is start specifying, the responses, the outputs that we care about at the end of our analysis. If I were to click on that table, you can see we currently don't have any. So what I'm going to do is just click on this mass property, and instead of looking at mass, I want to look at volume, the total volume of my design. And the moment you accept it, it's there listed in your browser again. I can look at the displacement of this node, and I'll tick for it. Same again, I can do the same with the stresses in my components. I care about the stress in this component as well as this component, and then you can specify a load step that you want to get the results from. And once that's all done, we can click on accepting it, and you can always review these in the entity editor. So you can look at volume, displacement. Again, we can assign a load step to this one. We can specify the magnitude and whether if we want it to be the absolute maximum or if you want it to be the XYZ component. And same with our stresses. You can specify, obviously we've already specified the two properties, and we can get the response component out of it too. Now once we've specified all of our output responses that we care about, we can tell the solver algorithm to solve for our different designs. At this point, if we were to click on the play button by the evaluate, we can see that we can specify our DOE type. So if you're looking at a full factorial, that's looking at your whole design space. So this is a screening algorithm, whereas MELS is a space filling algorithm. So if you just wanted to understand a good sample size of what your designs look like throughout its variety, then you can use MELS. I would recommend that you go and do a bit more research into the algorithm types so you know exactly which one you want to look for. Now I just want to get a good sort of sample size of my space filling algorithms. So I'm going to select MELS in this instance. And based upon the number of inputs you have and the outputs you want, it does go through an equation to specify the minimum number of runs that you should go for to get good results. So let's just leave it at 40. We can have it so that it can solve 5 jobs at once. There isn't a limitation on this, just make sure you don't set your laptop on fire. I can choose my OptiStruct solver in this case, and a solver argument would just be the arguments that you want to use with your solver. So in this instance I'm going to put -nt space 6 because I want it to use all 6 cores of my computer to solve. Now at this point what I'm going to do is just click export, and I will click run. From here you'll see that we have an evaluation status bar or table, and through here it will show you exactly when something's processing, when it's pending, and once it's gone through it will solve itself, and once it's done and extracted everything that you needed, then the status will also turn green. So let me try and enlarge this box and expand it further down. And what's also really nice is that without you having to change your solver deck yourself or vary your model parameters and go through and then extract everything, instead of that long, lengthy manual process, HyperWorks here will do it all for you. And where we saved our folders, where we saved our file, so remember that we mentioned the demo folder earlier on where I saved this DOE into. In the demo folder, all of the variations that it's creating, you'll see that it's put them into new folders for you, and it will also have written out the solver deck that you'll be needing. So in Model 1, we can see it's written out the solver deck, it's got the animation file, and HyperWorks is going through to extract those values for you. So you don't even need to, after understanding your data, you don't even need to go and make your model again with the right variables. Your models would have been made for you, and all you need to do is head into the right folder to use the model and use the design that you need. So let's just let this solve in the background, and once everything's done you'll see everything will be green. Okay, so once everything's solved, you see everything's green, what we can do is close that table and click on the triple I icon. Once we click on that, this will load up all of your different results from that design exploration. You can see the different values of your inputs, so all of your thicknesses, from the seat tube thickness to the top tube thickness, and you can see the respective outputs as well that you've selected for. So you can look at the volume, the displacement, the stresses associated to each run. Now we can also start looking at the linear effects as well between your data. So to actually really understand your data, you can see just how your inputs would affect your outputs. You can look at the relationships between them, whether if they're positively correlated or negatively correlated. You can see at this point, say if we were to increase the thicknesses of your different tubes, this in turn would obviously increase your volume. And from there you can see it with the positive contour and the colouring of your plots too. Same again, we can look at stresses. So if we were to increase the thicknesses of your different parts, you can see there's a negative linear effect on your output stress results. So you can see that the thicker it is, the lower your stress will be. Now at this point in time, obviously you can look at a different response, you can look at displacements. We've already covered our data and linear effects, but you can also plot for the trade-offs as well as the scatter plots as well within your results. So if we were to click on the trade-off button, what this is doing in the background is that it's applying a surface fit to all of the data that you have. So where you see these different sliders, it will show you where you could slide to any different values, ones that you might not have actually solved for. So you can slide it to any values, and through the given data that you already have solved for, it will look at interpolating the results between them to get you the responses, so you don't need to go through and run another analysis solve all over again. So where we can put the different slider at different values, this in turn calculates your response values, and obviously you get the R-squared value at the end to show you how accurate those values are. And if we go back to our full set of data, we can look for where we have the result with the highest volume, and if you were to right click on it, you can also load the results. This in turn will launch up Hyperview in the same session, and it will show you a contour display of the different results you have from the different solves that you've run for. So from here you can look at the displacements, the displacement contour, but you can also then change this displacement contour to looking at a stress contour instead. And where you can see the values of your different contours, and if we were to play our animation, you see that it doesn't really deform too much currently. So what we can do is head into a specific tool called Deformed, and through here we can specify a graphics, deformation, contours, and magnification. So we can magnify it by, let's say, 100 as a scale factor, just so you can see exactly where our frame will bulge throughout the analysis. And you can see how it's buckling to one side, and there where your maximum stresses are. Now from this point, what we can also do is actually visualize our plots. So we're going to divide off our page into 3 separate windows, and in this third window what we're going to do is launch up Hypergraph instead. And in Hypergraph you can plot your chart data in a lot of different ways. Today we'll be using the line chart, because what we want to do is look at the scatter plot, and along the x-axis we can specify exactly what it is we want to look at. So we can look at the down tube thickness versus our stress values, and you can see exactly the pattern between the different thicknesses you assign your part to be and the stress values you get from it. We can look to plot something else at this point, so we can look at, same again, the down tube thickness, but this time against the volume, and where from these scatter plots you can see if there's a positive correlation between your data as well, where the thicker it is, the higher the volume. Now if we're just going back to looking at all of our different results, we've conducted a DOE, but what we can do is duplicate this DOE that we have and actually turn it into an optimization instead. So the difference between a DOA and an optimization is that with an optimization, you're giving it a direction to how it can give you an optimal design based upon what you're looking for. So same again, in your Design Explorer browser, you can find the optimization run that you want. We will then assign some objectives, so we can give it a response of the volume, where we want to minimize this volume, but then we want to minimize this volume with respect to some constraints. So what I can do is create a constraint against our stresses, where we can give it an upper and lower yield value. And this yield value can be, let's say, 250 in this instance. And if we click OK, you'll now see we have 2 new points here. So we want to minimize the volume, but ensuring that our stresses don't exceed over 250 megapascals. And at this point, same again, where you can click to solve. Number of runs can be 50. We can give it multi-execution. Now I just want to solve this very quickly. So let's say that I only want it to run for 10 runs, and I want it to give me the best design out of those 10 runs. You know, which design gives me my objectives and constraints. Again, I'll specify it to solve with 6 cores. And I'll let this run in the background very quickly. Okay, now once this is all done, you'll see everything's in green again. Same button. We'll just click on the I values, and the difference between an optimization and a design exploration that we just conducted is the fact that what we're doing is giving the solver a direction as to how it should vary your different input variables to achieve the optimal targets that you wanted. So you'll see anything in green tells us that's our best design that we've got, and it'll tell you the best iteration, the condition, whether if it's feasible. And because we know that this is feasible, it's optimal, it will show you that this is our best design out of all of the 10 runs that we've done. Same again, you can right click to load your results, and it'll bring it up in a new window for you. You have a few more other graphs that you can look at, so whether if you want to look at your evaluation plot, your iteration plots, and you can also then again look at a scatter plot between your data between them. And this is Design Explorer in a nutshell. Thank you very much for listening to this demo.
Thank you, Joyce, for the presentation. I'm now trying to get back to my screen on that. Yep, it is live now. So there are some questions that popped up, and Joyce, are you in the call still? Are you muted?
I am indeed. Hi.
I am. Okay. I think I'm actually not sure if everyone can see the questions and answers in the audience, but can you just explain a little bit about the 2 questions that popped in here that I saw?
Yes. So one good question that we got was asking if you can register third-party solvers to HyperWorks. You can indeed register the third-party solvers to them. So you don't have to use OptiStruct, but within the setup of using your solvers, you can always add either to use LSDyna or Abacus or PamCrash. You just need to make sure that you refer to the right installation bin file that you're using. And then the second really good question as well was that we were asking if we can do curve fitting in here, not directly in HyperWorks, but with this study archive that you have, you can take it out into HyperStudy to do a curve fitting.
Okay, thanks. And of course, you may check as well if the export of say DAX in the other solver formats are supported, and that is for sure the case in the full software edition that we give to student teams. All right, so there's another question just jumping in as possible. Okay.
I see as well. Is it possible to do a topology optimization for each part so that we have variable thickness? You don't need to use a Design Explorer for that one. Within HyperWorks directly, you can just launch an OptiStruct optimization. So with your topology optimization, that's more mapping out the load paths for where your parts are being held to where the forces are acting upon it, to how it's being used. So if you did want variable thicknesses, it depends. If you're looking at sheet metals, then you can conduct a gauge thickness optimization, where you can look at uniform thicknesses across each part. But if you want to do a topology optimization, you can use that to just change your concept design so that you're removing redundant material out of where it's not being used.
Okay. I just get a question here that audio is not working. Miodrag, it's difficult to explain that through my mic because you're not hearing me. So I hope, wait a second, Central. Please check the audio settings and go to, sometimes it swaps the sources during the webinar. When we switch from a video to a live presentation, then some attendees see that. I had that myself as well one time, that GoToMeeting swaps the audio source and then you can't hear us. All right. Thanks, Joyce, for the answer. Is there anything else? Please put in your question into the live chat or into the question box. And in the meantime, I want to run a poll that Jens created and prepared. And I hope that is now up and running on your screen. And that is the question, if you have worked with data, if data analytics is part of your curriculum. So please tell us if these, say, data analytics, data science is already or will be implemented in your studies, as that is for sure a key part in the future, which enhances the development of classical mechanical systems and as well as smart products and so on. So we want to know how far you get in touch with these topics. Okay, it's more or less 50-50 when I see the share. Okay. Jan, are you in the call? Do you know 50%? 52 say no, 48 say yes. It's not yet, it's not moving anymore. I think I can close this poll, and I only 30, oh, here I see that 37% of you voted. So that is below 50%. So please give us your yes and no. That's just one click. And that's so that we get an idea how far these new topics are implemented in the curriculum as well already. Okay, so it's not increasing the number. So I turn off close the poll. And thank you for your participation in that poll. And I'm now going, if there's no other question here, no, then I will switch to the next presenter after I have thanked Joyce to participate here live and via the video, because I think you are heading out to a customer meeting now, and so thanks a lot.
Thank you very much. Thanks for having me, guys.
Thank you. Bye-bye. Now, the next topic and presenter is Marco Schmidt. It's a very interesting topic. It's about telemetry data. So whenever we talk about data, they have to come from somewhere. And telemetry is one source. And telemetry is used in racings, car racings, and as well in Shell Eco Marathon main races. So Marco is part of the technical team at Shell Eco Marathon, and he gives an overview about the infrastructure, how these live data make the overall race more exciting, and later on, how these data can help you to drive the next design, and this path is described. So this is Marco. He is from Schmidt Electronic in Switzerland. He graduated 92 in mechatronics and is an entrepreneur, CEO, does technical sales and focuses on digitalization and digital transformation, coach and leadership team, and working with Shell together. So he is as well live in that meeting. So after the presentation from him, feel free to ask him questions and he will answer them live.
Hi and welcome. I'm Marco Schmidt from Schmidt Electronic, and I want to show you today how we use telemetry in data-driven racing in motorsports. And now we dive into a very special community, I tell you. It's the Shell Eco Marathon. That includes 10,000 students coming from 800 universities from 50 countries. And there are visionaries. They kind of make room for innovation, make room for the new. There are very competent technicians that make sure everything works correctly. They are kind of the backbone of the event. And then there are our athletes. They are our heroes. It's the drivers, it's the teams. Everything is revolving around these guys on these events. So you see what kind of vehicle they are driving. We are talking about highest energy efficiency here. So on the top right, you will see what we call the prototypes. They're very sleek, high-tech, and they deliver the highest possible energy efficiency, while on the lower left, you see more the practical approach, the urban concept class that is made for real-life applications, and then the drivers. And to give you an idea of the extraordinary results these guys achieve, imagine a distance from London to Rome and back. And boy, imagine they make that road with 1 liter of gasoline. That's impossible, isn't it? So that means if you compare that to your daily commute to and from work, you make the 20 kilometers with just 1 teaspoon of gasoline. And what I like most about this event, it includes internal combustion engine, hydrogen cars, as well as battery electric. So it's a combination of all the 3 energy types. My role here is twofold. First of all, in between the seasons, I give presentations like that, learning sessions. I promote the data telemetry off-track award, give webcasts, and when I'm at the event, I am the technical guy, squeezing into the engine compartments, get my hands dirty, prepare the telemetry system hardware, give instructions to the teams and help them, coach them how to use it. And that's my role. And all I can tell you is that sustaining energy and clean mobility is very close to my heart. And that's why I attend the Shell Eco Marathon as a volunteer since 2016. Yeah, and besides that, I'm the CEO of Schmidt Electronic, who happens to be a partner of Shell Eco Marathon. And this is the kind of the connection that we have with Altair. We both are Shell Eco Marathon partners. And what we deliver here is we deliver electronics that powers the telemetry system that includes prototypes, MVPs, and series products. And as you can see, we are also a partner of National Instruments, NI, that happens to be a global player in test and measurement. Yeah, what's all about data-driven racing is we really want to transform the races. We want to transform the drivers. We want to transform the teams. We envision a competition that kind of follows a data-driven approach, that digitalizes it. We also imagine that we can innovate the driving strategy and the driving tactics. And overall, we are thinking about, thanks to data-driven approach, to increase on-track performance while at the same time increase the energy efficiency even more. And see, today we'll find out how far this goes. Underneath is a technology that we use in Industrial Internet of Things. We look at the building blocks of the IIoT. It starts all with a digital twin, a cloud server that holds a digital twin that is asking now for data that it receives from a bunch of sensors that are out in the field, out on the edge. And then finally we visualize the data, we kind of process the data, and we even apply some data science on it to get predictive results. This is, I would say, the building blocks, the underneath scheme. And now we apply Internet of Things technology to telemetry in motorsports. So here the sensor is a car that sends data to its digital twin. We make a live visualization so we can see where the cars are on the track. We do some data processing to analyze the performance of the day, and then we do some data science to get some predictive results. And what we do now is we dive into every piece of that building block and see what happens there. Start with the cars that are connected. We have the energy source. We have the driver. Then we have in the embedded systems that connects to internal sensors using a measurement network. We have a relay that with that we can stop propulsion at any time. We have a GPS receiver, and we have an IMU and many, many sensors more. But these are the essential ones. Now let's deep dive into the embedded system and what are the building blocks of the embedded system. So you can see there's a bunch of functionality that is on a very tiny board that connects the board to the internet, that connects to the internal sensors, has a lot of functions in it, is powered by a very strong microcontroller. And then this board again is installed in a small 3D printed housing that is put on top of the vehicle to get sensor data from there and connects this vehicle to the internet. Now let's have a look at the energy sensors. It starts with the liquid flow meter for internal combustion engine. So here we have the liquids going in and out, and we have a system in there that measures many thousands pulses per milliliter, makes it very accurate. And there's also temperature that we are going to measure in order to compensate for it. In order to make that smart, we bought a commercial sensor and put in a specialized version of an embedded system that kind of converts the physical value on site and makes them digital and send them to the embedded system via CAN. That is pretty common in automotive industry. And what we receive from here is the used milliliters that are used while the engine is on the track. And here we see how it looks like in the compartment. We see how the fluids go through the sensors, and on the right hand side how is it connected to the embedded system through a CAN bus. Battery electric uses a joule meter. We see here the two bars. They are connected to the battery terminals, so we measure the current going through these bars and the voltage that applies there. So from that we measure the power, and from there we get to the joules. And again, the same technology is used. We put in a smart board, an embedded system that makes the sensor smart. So in order that we convert the physical value on site directly into digitalized value that are sent to the embedded system through CAN. And this is how it looks like. It is installed in the battery electric cars. And then we have the gas flow sensor used for hydrogen to see how many liters, normalized liters, the fuel cell is consuming. And this is again installed in the engine compartment and connected to the embedded system. And now we have 3 sensors depending on the energy type being used. Last but not least, GPS. At first it seems very easy, I would say easy sensor acquisition, GPS data. However, you need to know that in order to get proper GPS signals, you have to have a direct view to 7 satellites, and this is seldom happens on the track because sometimes we have high-story buildings beside the track, We have bridges, crosses over the track that kind of leads to dropouts of the signal, or maybe deflects it and reflects it, and this leads to faulty signals. And there were some funny incidents on the track. So we have seen the vehicle was really on the track, while on the big board of the visualizations they were really moving in a nearby shopping mall. And I remember the headaches we had in Detroit, in the canyons of these high-story buildings. This was really a nightmare, and as you can see on the first measurement that we took before the race, there was a high distortion on the GPS longitude and altitude, and there was a lot of work necessary and improvisation to make that work. So I would like to use GPS data now to show you the flow from the sensor and how this physical value makes it through the whole stack of software until it arrives at the cloud. So it all starts with a GPS signal that is picked up by a GPS sensor. There are a lot of commercial variants around there, for example from u-blox. And this GPS sensor translates the signal into the NMEA format, which is pretty tricky to read, but if you know the structure, you can immediately see the longitude and latitude there. And this is then kind of fed into a service that only picks the relevant information there and copies it into a new data format, a data format that is then sent to the main program that handles this information. And together with other information, kind of generates a data stream to be stored on a local CSV file. Or we translate it into JSON format that is really common in this in applications like that. And through MQTT, we send it to a cloud. MQTT stands for Message Queuing Telemetry Transport, also pretty common in IoT technology. And so here we see the stack. How the sensor values makes it up to the cloud, and we not only have GPS, but we also have the joule meter, the liquid flow meter, and the gas flow sensor, and all this data is then aggregated in a main program powered by the Linux operating system. They were program written in C, and so this is now what we call the embedded software that runs on the embedded hardware, and together it's this embedded system that produces the data points. And here it is installed on the car. A car that is moving around the track. So we receive now sensor data, send the sensor data to the cloud, and this is where we go next. So the cloud service with a digital twin starts with receiving data packages from our embedded system through an MQTT broker. A Kinetic server picks up these data packages, smooths it, validates them, massages the data, and makes sure everything is good, everything is how we want it, then stores the data in a database for further usage. We also update the monitoring health system to see everything is going right on track, and then we push data to visualization services. We soon get into these ones. And the Kinetic service is really, I would say, the heart of this cloud server. It uses an underlying node map that we always model when we go to a new racetrack. And as you can see, it's evenly divided. With evenly divided distances. Also the start-stop line is modeled here so that we can check, is a car on track, is it off track, how long does it is on the track, what's the distance traveled, and so forth. And then data is ready for visualizations. So first of all, we have what we call the Embedded Systems Manager. Here, every embedded system is connected to the manager. We can see if it's green, it's good to go. If it's yellow, we need to do something. If it's red, it needs immediate correction. And what's really great, you can really then zoom in and drill down and see what's happening on the component level. See, is it the temperature that's not going good? Is no fluid going through the liquid flow meter? So it's very easy to pinpoint the problems. We use it every day as a technicians. We walk around, we look into these telemetry systems. So we have literally their digital twin in our hands. Like on the left-hand side, these guys are now queuing up the start line, and we just make sure is that everything got a green light. And on the right-hand side, the guy will check the car first before it's allowed to go out on the track. And now they're out. We keep tablets in our hand, see that energy is now consumed. We look at the status signals. Is everything green? That's good to go. So we know that everything that the prospect is seeing on the big screen is running well. And this is what the prospect is watching. So we have the live leaderboard on the left-hand side. We have on the right-hand side this live map where we see exactly where the cars are, who's first, who's last, what lap they are, and what remaining energy they have. And it's really great. And finally, the last lap is the most exciting one. So there's tension, drama, while you see the cars moving towards the finishing line, and everybody's wondering who will be the winner of this competition. So much for live data. Now we look at the end of a race day. There's a lot of static data that we want to process and analyze to see what is going on. Can we improve something? That means a lot of data is stored in a CSV file and in the database. And what we do now is read the files and pick out the exact data that we want. Something like joule meter data that is sampled at 10 Hertz. So on the left-hand side, we see the volts, the amps, and the power, while on the right-hand side, we see the accumulated joules. So that means if the car goes out, while he's on the track, energy consumption goes up, and sometimes we see a peak like in there, and then we see maybe he has put too hard on the throttle, and that used more energy than anticipated. So this is the first easy to use analyze method. Liquid flow meter, gas flow sensor. Here we also measure the temperature. So that means if the car goes out to the track, the engine compartment gets hot, temperature rises, and then we need this temperature to kind of compensate in the smart sensor itself. On the right-hand side, you see the instantaneous flow on the lower part. So here we have, if you hit the throttle, you accelerate, then you use more energy. So you get these energy spikes. And this leads to this cumulated flow that you see in orange on top. And this orange line also shows these ripples, and these ripples are directly connected or linked to the spikes we have in the instantaneous flow. We also can plot the longitude and latitude, which, okay, doesn't make a lot of sense because we see here, the trajectories. But what would make more sense is that when we would have the race line for each lap. And now we move into the data science to make that happen. So what we first do, we add the start line, stop line, and the lap line, and that allows us to split the trajectories onto the different laps. So every lap has now a different color, and this allows us now to estimate or to analyze the different lap and the race lines. So like on the left-hand side with internal combustion engine, you see the energy consumption per lap. So you can see on a lap-by-lap basis how you do, and on the right-hand side, the battery electric. And this really helps to see what was your first best lap, what was your worst lap, and maybe what did you do in between, what was the driver doing different. And at the same time, it's still, I would say, challenging and tough to really understand what's going on the racetrack itself. And this brings us to these facet plots where we kind of lay out all different laps. So you can see at a glance what's happening, where you have the long burns, where you have the tight short burns, how you did corner 1 in lap 2 compared to lap 5, what did you do differently, and how this led finally to these differences in energy consumption, and to get to ideas to make your runs better. Brake-specific fuel consumption is another data science method in order to find the best target region to operate your vehicle. So we have the vehicle speed against the road load force, and this certain region where your driver would create the best results. You can use other commercially available tools such as NI LabVIEW to analyze the data, to get out more meaningful information. There are the strong and very advanced Altair tools like Panopticon that allows to analyze the historical data and also live data. So, but what's important, what I wanted to show you today, how we can really leverage race data through telemetry, through this kind of generic building blocks to get what we want, to get the information that allows us to improve our results. So the presentation I gave you today We also, as a data technology TV, provided one to the students earlier this year with the idea to kind of motivate them to use data to make their results better. And what we received was really astonishing. So we received about 50 submissions and they were really inspiring and kind of fell into three categories. The first categories, they were creative. So they used really cheap and economic platforms to, at the same time, get some sensor data and send it to the cloud. And on the top right, you can see how they used analytics to compare the results to kind of estimate what energy efficiency they can achieve with a telemetry system. The second category used digital twins of the cars and of the racetrack. They kind of come together in the cloud in order to find the best racing strategy that is then downloaded into the cars. And the third category here, we felt like being in the Tony Stark's laboratory, where the driver is supported by high-tech assistance systems that shows him exactly which race line to follow in order to have the best possible race line. So that allowed him to completely focus on what's happening on the track, to overtaking and stuff. And that's really fantastic. And that this kind of motivated us again to move down that path, to kind of follow this digital transformation of race teams and driver, and following the vision that we can, with the data, improve the strategy, improve the tactics, and that finally leads to a higher energy efficiency, while also maybe increase the track performance as well. Yeah, that was it from my side. I hope you enjoyed it. Thank you very much for coming. If there are questions afterwards, fire away. Otherwise, I thank you again and wish you a great and inspiring Congress and webinar. Bye-bye.
So thanks a lot. I have to share now my screen again. Yep, should be now shared. I have to manage my screens here. So thanks, Marco. You're online as well. Are there any questions? I have not checked yet, but I will. Where are they? Regarding telemetry. It is really interesting and to see how you work with Michelle Ecomarathon to enable the teams to get there and connect their data and make them available later on. And I'm sure that these teams will value these data as well and use them later on in the, say, next year, next season development. So, any question from the audience? Hey, Marco, you're in?
Yeah.
Okay, so is there any, oh, Shubham? Okay, did you see the question? What weather conditions or do weather conditions affect the collection of the data so that they are accurate? That's a good question, actually.
I just need to think about that one. Weather conditions, not so far on the GPS side or on the energy sensors that we install. However, mentioning weather, this is another sensor that we want to add to the system so that we kind of, also when it comes to wind, and find out what is the influence of wind changes and stuff. The only thing that comes to mind when weather comes into place is about safety. For example, when it's going to rain, there's a lot of rain on the racetrack, then they stop the race anyway. But now, collecting of the data is just actually, because I mean, we use 4G, we use Wi-Fi to transmit the data from the car to the cloud, so that's independent on the weather. And GPS receive, yeah.
Because sometimes I would say not Wi-Fi, but at least 3G or 4G service from Telekom here in Germany, that is at some areas dependent on weather sometimes. So,
Okay.
but during the race, you have no issues with that.
So another question here: what are your visions to have for improving the race data analytics in the future? That's a really great question, because we really we have no experience yet on it, because we started at the beginning of the year with the students, and when we look at the estimations and simulations, we expect improvements of something like they start with 5% until 18%, just by using data to improve the strategy. So not changing any of like the construction or something like that, just by applying data to do a proper race. So this is in the lower or in the higher one-digit range of improvement, indeed.
I mean, these live data, that affects the strategy as well during the race, and that is important. That is an important outcome as well, so that you know what's going on with your vehicle, with the driver on the field, and then you can manage the tactics and so on, and that is important.
I mean, you see it in the three categories. You know, the first category, they were very simple. They were looking at the data, and then a team outside of the track was analyzing the data, and then they radioed back to the driver and say, now go a little bit slower, or now you can increase your speed. The second one that has these two, the digital twins that kind of create a strategy, and the guy in the car followed that strategy. So he knew in corner 2 he can go full speed, while in corner 8 he must be slower. And the last one was really conceptual. So these guys envision something that on every meter on the track, the driver knows exactly what to do, and being supported by this computer model. And so he concentrates more on maneuvering the vehicle, like overtaking and stuff, while he gets the full support that the race vehicle is following the best race line.
So it's really making difference, and so as well, I mean, the design, the construction of the vehicle is important to be successful, but the full team effort, the full team strategy is as well important, and through these live data that can be how do you call it, used and utilized a lot more and influence the success of the team.
So there was another question coming in: what role will data analytics play in the everyday cars that we will drive? If I could have a wish and a vision, I would be that we would have the best energy efficiency that is possible on every meter covered. That's why I also support the Shell Eco Marathon, because I still think that you use too much energy in today's driving into those commercial vehicles, and that thanks to data analytics that we get to the best possible results, while at the same time get necessary performance. And I mean, this is what it was all about, the goals that we have. We want to have a good performance, yes, because we want to get from A to B very quickly, but at the same time have the lowest possible energy consumption.
Yeah, that's my wish as well, to see that this technology helps us to reduce energy consumptions to really a minimum, and that's actually, yeah, it's a good vision to have, and everyone is working in that direction. So thanks for the questions here. Thanks for answering, Marco. You may be around as well if some questions will pop up, or let us know if you want to drop out of the meeting. Let us know. But in the meantime, we are now proceeding to the next presentation. It's about dashboarding, Actually, we are really happy that Marco helped us to get access to historical data from arrays so that we could use them to create valuable dashboards, and so that we understood what values come in, what sensors are measured, what things are measured, data are measured. And this is what we want to show now. So Naman took these data and he created a dashboard to show you in the next presentation how to do that by yourself. And you can do some actions as well, driven by the data coming in based on some logics you define in kind of real time. And these data can be, or this dashboard can be, say, developed by historical data. You can actually simulate a live event and later on hook them actually to the live data stream coming in. It's based on Panopticon here in the way that Panam used it. Naman used that. He used a kind of a standalone installation, and we'll see later on in the next presentation that Panopticon can be, say, embedded as well in a wider environment platform, but that is for the next presentation. So here for the next presentation. Now, Naman, he is placed in India currently. He is working as an intern in our team and is helping us to create these to explore the dashboard, to explore all the possibilities we can later on supply and give you access to as a student team to dashboard your data, live or historical ones. Naman is in the call as well as a panelist later on, and he can answer questions as they come in.
Welcome to an introduction to data analytics and dashboarding using Panopticon. I'm Naman Fairwani, a student intern with the Global Academic Program at Alta Engineering. Data everywhere, not a way to see. Imagine driving a car with no speedometer, but instead you get an Excel sheet with all your speed logs. Now, does that help you? No. Is that safe? No. Well, that's what dashboards are for. They help you visualize your data in an uncomplicated, untroublesome, convenient manner. You can store and organize multiple data sources in a single, easy to access place. Now, this can help you to get a better insight into your data, where you can view critical pieces of information just like you can with the dashboard in your car. You can focus on the outliers. You can add alerts and monitor risks, all in real time. On the screen now, we can see the kind of dashboards we can build using the data visualization tool Panopticon. On the left side is a dashboard wherein we can monitor over 10,000 commercial vehicles, all in real time. We can check on their operation, fuel consumption, actual speeds, accidents, and route deviations using connected car telemetry. We can also make comparisons with historical data and compare each vehicle's performance with its peers and flag the outliers. On the right side, we can see the visualizations of telemetry data from Formula One cars. Panopticon accepts real-time telemetry data from race cars and applies a series of statistical functions on the fly and visualizes the results. Now, applying analytics to racing enables faster, more accurate decisions. Panopticon offers a code-free dashboard development option for data visualizations. It has a user-friendly drag-and-drop interface with a universal connectivity to any data source. With such analytics, we can monitor risks, reduce operating costs, and hence increase profitability. We can use the dashboard for a lab-to-lab, car, and driver analysis. We can keep a check on the car health along with its structural and aerodynamic performance. Now, similar to a car dashboard, we can also observe the engine temperatures, tire pressures, and set control metrics. With onboard sensors and telemetry, we have a diverse set of factors we can analyze with dashboards during racing. We can combine the historical and real-time data for fault detection, set alerts to predict potential failures, say the brakes, tire pressures getting too low or temperature going too hot, and plan proactive maintenance. It also enables us to drill down the data and compare previous races, cars, different designs, laps, competitions. During developmental stage, we can process and analyze different sensor metrics from wind tunnels in real time for direct correlations, improvement, and benchmark analysis. A high-frequency time series analysis can help optimize engine performance. And we can extract information from multi-structural file systems, say the race results or the regulatory data, in a PDF and CSV format. Now, the two main problems with telemetry data and streaming are big data and fast data. The input data, be it the raw telemetry data or the sensor message, it is impossible to use it for visual analytics as it lacks dimensionality, it is too granular and high frequency in nature, and it needs aggregate measures. Thus, dashboarding helps aggregate the data, include calculated columns, rank the data, and divide it into mini batches or even combine batches of data to provide flow and accessible granularity to the data. The analytical approach taken here is the focus on anomalies, identification, investigation, backtesting, and optimization. These provide a platform to build better dashboards for data discovery and insights. Dynamic reporting, along with universal connectivity, helps in using the data for what it is meant for. Now, to start building dashboards, simply add your data sources. They can be Excel sheets, text data logs, or even cloud-based on Panopticon, and you're good to go. Use historical data or stream live data and drag and drop to add visualizations. Panopticon's content repository structure allows you to share your dashboards between servers and even on the cloud. Let us now check out a case study of data visualization of the Shell Eco Marathon. The Eco Marathon is a student engineering competition focused on energy optimization. Started as a wager between colleagues to see who could get the best fuel economy from road cars adapted to maximum energy efficiency, the track competition today has come a long way. The teams now can choose from an array of energy options: battery electric, conventional IC engines, and hydrogen fuel cell. They can use different materials, from advanced carbon fiber to bamboo, and optimize their vehicles for this mileage-based competition. The vehicle performance is monitored continuously using various sensors. Liquid flow meters are used to measure the fuel consumption in IC engines. Gas flow meters are used to measure the hydrogen consumption in hydrogen fuel cells. And joule meters are used to measure current, voltage, and net joule usage in battery-operated components as well as the battery electric cars. GPS coordinates and other GPS-derived data, such as speed and distance covered by the cars, are tracked also. The telemetry data is made available to the students in the specific Team Online folder a minimum of 2 hours after the end of the race or an attempt. Teams can use this data to do a post-race analysis and make improvements. The dataset given by the event organizers is of the following format. We have timestamp readings from the onboard computer system as well as from the GPS. We can see coordinates in the format degree, minutes, seconds north, for latitude and west for longitude. We can see the GPS-derived data, such as speed and the distance covered by the car. There are also readings provided by the Joule meter and the liquid flow meter. Let's start building an interactive visualization with Panopticon. These visualizations automatically handle your aggregation, time series data, filtering, sorting, and many more. At its core, Panopticon allows you to connect to various sources of data like Excel spreadsheets, XML, CSVs, databases like KDB, Kafka, and more. Let's jump right into creating a dashboard. After logging in, this is the homepage for Panopticon. The tabs up here help you manage the aspects of the Panopticon homepage. We're going to use the Workbooks tab right now. As you all can see, I already have a few example workbooks here. To create a new workbook, you can simply click on New Workbook or right-click anywhere and select New Workbook. Let's rename this to Car Telemetry. Click Create, and you will be taken to the Panopticon editor. First, let's get an overview of this page. The editor is divided into 3 different sections. On the left is a data table, which is currently empty. On the right, we get a preview of our visualizations, and in the middle, we have a contextual menu on what we're currently doing. So the first thing any workbook needs is a data table. Let's create one by clicking on this plus button and adding a data table. You will be taken to the data importing screen. Over on the right, you can select which data source you want to use. Today, we'll be using an Excel spreadsheet. So to import one, I can click on MS Excel. I can browse for the sheet I intend to use. Let's rename this to Car Telemetry. Hit OK. Fetch sheets. So our data is loaded in, and we can preview it by clicking on Refresh Preview. We can preview our data at the bottom. If you want to rename any column, you can click on Columns. All the titles of the columns are up here, and simply rename that. Let's rename this to just ID. Hit OK. Refresh. Panopticon automatically identifies the data type in each column. The data types that Panopticon allows are either numeric, text, or time. Let's change the data type for the column ID. Let's change it to text. As ID is different for each row, turning it into text will help us break down the data, as we can see later. Hit on refresh. We can also change the format of the time display. I'll use the hours, minutes, seconds, milliseconds format for the OBC timestamp. Hit refresh. We can see the change in format. If you want to apply any transformations to the data, there are some pre-built options here, including custom Python transformation, as well as the very important transformation to enable time series analysis. Since the data that we have today is time series dependent, let's enable this. Let's unselect these and these. As the ID column is different for each set of row, this will help us break down the data. Hit refresh. Additionally, we can see that there are some settings over here that can help us change the refresh period. The refresh period is how often it goes and gets the data. We'll have a look over it later. Well, here we go. Let's go ahead and save this. And let's head back to the Panopticon editor. We're back on the editor screen. The data that we imported is on the left side of the screen. With the help of this button, we can toggle between the view and the edit menu. With Panopticon Editor, we have two built-in themes, dark and light. Let's stick with the dark one. And let's create a first visual. Simply point your cursor anywhere on the screen and select to create an area. We have a variety of visualizations to choose from. As we're doing time series analysis, let's choose a line graph. We can see the format on the x-axis for time. Let's change it to the one that we need. We can customize the endpoints to the format that we need. Similarly for the tick points. Now tick points are the values that you see at the bottom of the x-axis. Let's customize these as well. Unselect this. On the y-axis, let's try to plot GPS speed. There we have it, our very first visual. We can modify this graph a little bit by giving it a title, say GPS speed, hit OK. We can change the color of this graph. Simply drag GPS speed to the color menu and select the color that we want. Let's try this. We also have an option to add a reference line. Simply click on reference line, add a constant reference line. We can add the value that we want, say 3, hit OK. We have added a reference line. Let's change its color to bright red. We've added a reference line as well. We can create similar plots. Simply select an area on the dashboard and select the type of visualization. Let's again try the line graph. We can change the format on the time axis for this one as well. This time let's try to plot the net joule usage. We can change the color of this one to green. And in the general settings, let's give this graph a name. Hit OK. And let's enable a few of these options. They shade the area below the line and they also show the last value, which in this case is 1412, which can prove to be quite useful. Let's try to create another visualization, a different one. Let's try to plot a group needle graph. Similarly, in this case as well, we can change the format of the time axis. And on the y-axis, let's try to plot the GPS distance. This, in this case, is a cumulative GPS distance. So, selecting a certain kind of palette, that is a range of different colors, will help us give a better idea. We have the orange shade for smaller values, while it turns green as the value increases. We can also add filter boxes here. This helps us control the time interval between which we want to view our visuals. Select an area, click Control, and add a time filter box. Select any column that we need, say net joule. We'll change the format of the one that we're using. And we can add a reset filter as well. And we can toggle between these values, and the graphs and the visuals will shrink and contract depending on the interval. We also have an option to view these values and these intervals. Let's try to create another visual. This time, let's try to plot the current and voltage on the same graph. Panopticon allows you to plot multiple variables on the same graph, and you can toggle between them for convenience. Simply drag the current and voltage to the y-axis. And there we have our plots. Now let's try to add a digital clock at the top of this dashboard. Simply select the area. We'll use this area later to fill in with the digital clock. To add a digital clock, we have to add a new data table. Click on the plus icon and add a parameter. Let's name this parameter current time. Current time in this case is a special parameter inbuilt in Panopticon that helps display the current time. Let the data type be time. Let's change its title to clock. And let the auto refresh be 1 second. The value will change after every second. Let the data source be text and let the text file source be text as well. We can add time as a column and let's input a variable there, current time. We can choose the format that we wish to display, say hours, minutes and seconds. We can now scroll down and click on generate columns. This will generate a single column with the time variable. We can see it here, but it's in the format of days, months and years. We can change it by clicking on columns and selecting the format that we need. Refresh preview. With each refresh, the value of time changes. Let's save this and head back to the editor. Select the part on the dashboard, click on General, and let's add a text label. Let the text mode be data, and we'll select the time column. It's in the format that we need. Let's tweak this a little bit. Change its color to white, and let's enlarge this by changing its font size. Well, there we have it. A very own digital clock at the top of our dashboard. Well, this is how we can plot variables on a time series analysis. Well, now let us try to do some other type of visualizations that are not time dependent. Let's go back to the edit menu. Let's create a new dashboard in the same workbook and transform this data back to its original state. Let's disable the time series analysis and refresh. That is the dataset that we had earlier. Let's save this and go back to the editor. Let us try to create some other type of visuals. Let's try to create a table. We can break it down with the ID. Now breakdown here helps Panopticon decide how to divide the data and helps with the hierarchy of the data. Let's try to add a few records in this table. Say the GPS speed, current, voltage. We can see all the data at once, and this can help us further analyze the data. Let's minimize this. Let us use this table now to calculate a few values. Create another visualization. Select table. Now in the record section, we can add GPS speed. We can add it a few more times. Let us use the first GPS speed to see the maximum value of it in the dataset that we have in hand. So the value is 9.08 meters per second. And the second one, let's try to calculate the minimum one. Minimum one's 0.83. Let us try to get a mean or average value. We have that at 6.51. We can do the same with other data types as well. Say for current, voltage, LFM instant flow. With the current, we can try to find out the maximum current value. Say for voltage, we can try to find a mean value. Similarly, for the liquid flow meter sensor that is measuring the fuel flow, we can get a summation value, that is aggregate of all the sensor values. There it is. We can create other type of visualizations as well, such as bar graphs, pie charts. Let us try to plot one. Select an area. Select a bar graph. Let us break it down with ID and plot the GPS speed. And there we have it. We can create various other dashboards and make them as interactive as possible with the same data source. We can do a lap-by-lap comparison for GPS speeds. You can add or deselect a lap. We can see a side-by-side comparison of GPS speed. We have an option to select a particular lap and add filters so that we see the values of different variables along that same lap. We can also plot the coordinates and get map plots. We can select a particular lap. They'll all overlap. Panopticon helps you visualize your data and helps you get as much information that you can from them. We did dashboarding with a static Excel sheet. With Panopticon, we have an option to stream data to simulate the racing environment. We can visualize real-time telemetry and monitor various metrics like the weather, brakes, tire pressures, suspension, fuel, throttle, and even driver analytics. We can also perform a lap-to-lap comparison. We can select different sections of the track and visualize specific metrics such as the car speed at turns, driver heart rate, and many more. With addition of an embedded video, we can also focus on footage from a specific section of the track. Let us now try to monitor a different section of the track with another bend and see the car's performance. The race summary graphs help us do a post-mortem of the race. We can monitor analytics of different teams, drivers in different sectors, and make decisions. With the help of rubber band selection, we can choose specific parts of graphs and see all visualizations related to that selected metric. Well, that's all from my side. Thank you for joining. Have a good day.
So thanks, Naman, for the introduction. Dashboarding, it's very interesting, and I'm pretty sure you're as well curious and excited to play around and work with that. I check if there are questions popping up. So Naman, are you in the call? I see you as well, at least as panelist. Can you unmute yourself? Does that work? Okay, anyway, I'm checking here the questions. Give me a second. Here they are. There are no questions yet. Directly to the presentation of Naman. And if that is still the case for the next couple of seconds, I want to say move forward to the presentation of Paloma. So she will introduce she will introduce smart product development with IoT, and how a smart product can be linked to an IoT platform easily, how to manage these incoming data, and as well derive decisions out of that. It's based on a cloud-based environment, our SmartWorks IoT platform, and you will see something in her presentation that you just saw before, and that is Panopticon. So Naman used Panopticon as a standalone product on his own machine. Now, Paloma will use dashboarding inside of a SmartWorks management platform, as well for dashboarding and to make decisions and drive decisions inside. So just a quick introduction of Paloma. She is a product specialist at Altair, sitting in Spain, and she was an intern, IoT intern, before joining us as a full employee, and she has a master's degrees of industrial engineering at Universidad I have difficulties with Spanish. Pontificia Comillas in Madrid. My Spanish is really bad in that. So thanks, Paloma. She's in the call as well, and will answer questions later on after her presentation, and you're welcome to type them into the question block, and then she can give you the answer at the end.
Hi everyone, I'm Paloma, and I am product specialist in the SmartWorks IoT team. Today, we will be talking about the smart product development. The purpose of this session is to show the solution offered by the SmartWorks IoT platform for the development of connected products and all the things needed to complete this process successfully. After a brief introduction, we will be analyzing a real use case where we have helped a motorcycle company to enhance its business development by using SmartWorks to build a smart product, and finally we will dive into the product itself. As you may know, over the past years, product development has been focused on product design and product engineering. But the new trends that have appeared made us start thinking years forward about the future of product development. So that's why we have evolved from tools that offer generative design, topology optimization, and mechanical and electrical simulation to smart product development, offering tools for embedded development, software development, and continuous improvement. You might be thinking, why does all this mean for any company, and why developing a smart connected product is something relevant for a business? And typically we have three main use cases, which are that you may want to improve your users' experience and give them control over the product. So imagine, for example, you are a motorcycle manufacturer company. It would be nice to provide your users, who can be owners, rental companies, or servicing firms, with an application that will enable them to monitor and control motorcycles on the field. Another option is that you want to offer your product as a service and therefore obtain recurring revenue streams, for example, as a motor sharing company. Or maybe you just simply want to improve operations and streamline processes and keep your assets running as long as possible, with the highest efficiency and the lowest cost. So if you are planning, for example, to take part in a competition, tracking the different parameters of your motorbike after each lap will be really useful, as well as having information in real time about how your system is performing. To achieve any of these goals, we need to develop a connected product, and this involves managing an ecosystem that is made up of different pieces. As you can imagine, this process can be a bit complex, because developing an IoT software ecosystem is not only about designing the front end, such as the web or mobile application that your users and yourself will use to track the performance of your motorbike, but it also involves edge, DevOps, and backend development, which are crucial pieces of the ecosystem. The edge allows you to manage devices in the edge, so you can monitor your motorbikes, update their software systems, and easily iterate on their design securely. DevOps will ensure that these services are up and running 24/7 and, if necessary, scale to meet demand. And backend is the one that orchestrates all the interactions between devices, users, and the logic required for the product itself. So this is where SmartWorks IoT stands out, as a low-code application development platform. Thanks to SmartWorks, the process of building the IoT software ecosystem mentioned before is simplified, while reducing costs and risks when developing your smart connected product. SmartWorks is the linking piece between all your devices, which are the motorbikes, and your end users, who just want to use a fancy app and don't really care about how the database is built, how the data is being collected from the different motorbikes, or how the management of the fleet is being done. If your use case scales and you end up having so many motorbikes you want to control, you might not want to go through the whole process of developing an application for understanding how your fleet of motorbikes is working. In that case, you just want to visualize the data you have been storing in SmartWorks and analyze it in real time to be able to draw relevant conclusions. And for doing that, we have Panopticon integrated to design powerful dashboards easily. If your use case gets more complex and you need to rely on heavy computing and the edge so that you are able, for example, to deploy complex machine learning models on your motorbikes, you can also use SmartWorks to help you deploy and manage all this code at the edge. In the end, what we offer is a modern, scalable, collaborative, and secure solution that provides modern interfaces for developers to create an application in a cloud-native architecture, so that you can choose your cloud provider and deployment infrastructure. All of this with modern languages and modern open toolsets that ensures that your product is scalable and performant from the beginning. What we achieve with SmartWorks is to do more with less. The application and the use case is still under your control, and we just provide the underlying tools so that you can be the best at your use case. And all this while ensuring scalability and security, allowing you to perform faster iterations and providing a flexible environment that adapts to each case. The features that differentiate SmartWorks from others are that it is a platform especially designed for product developers, so it has all the necessary tools for it. We are cloud agnostic, so you can deploy SmartWorks in any cloud service, so your data will be stored in the place of your choice. We can deploy on-premises to connect thousands of devices from multiple locations securely. And it is also integrated with other Altair tools, right now with Panopticon visualization and stream processing, but we are also integrating with the Activate tool and planning to integrate with many more. And finally, all of these come under the same units business model, which lets you take advantage of SmartWorks in the most convenient way for your business. To understand better the motorcycle use case or any use case, we can use Panopticon, which is integrated in a SmartWorks IoT platform. It is an Altair tool that helps to visualize data flowing into the platform. Thanks to this tool, you can have an overview of all the information that you have in the platform, perform analysis over it, and also see how you plan to show the data to the different end users. In this case, we have designed 3 different dashboards. Each one of them has the data to perform different analyses. First dashboard is the control dashboard. It summarizes the information that will be relevant to have control over the whole fleet of motorbikes. First part shows where each motorbike is located at the moment. The color is representing the health index, which is a parameter that we have created to set up how well the motorbikes are performing based on other parameters. To understand this health index parameter better, we have created a heat matrix chart showing how the motorbike health index changes depending on the different models of motorbikes and the year. And we also have a scatter plot to analyze the dependence between the battery and its capacity. In this case, size is representing the number of kilometers driven by each motorbike. And finally, we can also see the distribution of the motorbike speed related with the number of kilometers driven for the different years. These visualizations can be further customized by applying filters. We can choose to see, for example, the detail of this motorbike that has a real low health index. As you can see, the rest of the graphs have been updated with the information of this specific motorbike. Based on this analysis, we may conclude that some of our motorbikes might require some maintenance services. So that's why we have the supply dashboard. This dashboard helps us to know the current inventory, the demand we have, and the orders that we have made to meet this demand, and also their status. Also, information of the already inspections scheduled can be found here. Last dashboard shows the information that our end user might be expecting to have so that we help the rider manage their motorbike by showing the trip records, last trip, motorcycle status, and any scheduled inspection, everything in a single view. Now that we have the idea in mind of what we can achieve with SmartWorks, let's understand how all this is done. If you want to join SmartWorks IoT, you just have to search for swx.alterone.com. If you already have an account, just enter your username and password and click on Login. If not, let's sign up. Once you have verified your email, you can finally log in. Right after logging into SmartWorks, the following welcome page appears. First thing is defining a space for our project to live in. We are going to name it and click on Accept. Note that there are some restrictions regarding the space name. You just must enter at least 3 characters, and it cannot start with an uppercase. Note also that special characters are not allowed. Spaces work as isolated work environments to build the different smart product applications or projects that you want to host inside SmartWorks IoT. So you can keep on creating different spaces. Deleting a space is so easy. Just enter your space, click on Space Settings, General, and you can delete it. When we create our space, the name that we are setting is the ID of the space, but we can change this name. Enter your space. You can change the name that is displayed on the space card and over here. Uppercase I'll allow here, and also spaces and special characters. Check how the display name has changed. Last thing we can do from the space settings section is customizing the color of our space. That means the color that is going to be displayed on the welcome page. Once we enter our space, you can see on the left the different modules in SmartWorks IoT. Thanks to them, we will be able to set up our database, deploy custom logic, manage access control, and create dashboards in a collaborative, secure, and low-code environment. Inside AnythingDB, to organize our database in a logical way, we can create collections to group the different entities and enable fine-grained access control over it. For the purpose of this example project, we are first going to create a collection to store information about the different motorcycles. Next, we are going to add the first motorbike to the collection. Each entity can have a set of properties to define its attributes. For example, we can define distance to NTIP, so that we can know the approximate distance we can drive with the battery power remaining. We can also add actions that will help us define a standard interface for requesting commands like instructing the motorcycle to turn on the lights. And finally, we can also set events to define a standard format for reporting information, such as when the battery level is low, so that we are notified to charge it soon. We can keep on adding more properties to perfectly define the parameters we want to track from our motorbikes. Note that you should at least enter the title and the type of property. Once we have all the properties defined, we may want to reuse this configuration to create multiple motorbikes. For doing this, we just have to save thing schema as a model. Models are used to define a template to create new things easily and quickly. Click on the Edit Schema button and choose Save as Model. If you don't have a model created, we can just create a new one. Just name your model and click on the Add button. The defined thing schema will be stored inside this model. We can now check at the Models tab that the model has been created with all the attributes defined. New versions can be added based on this one if any improvements are required. The thing schema that we have stored provides a standard schema definition for the motorbikes that we are modeling. It is compliant with the Web of Things theme description and is built on top of the popular JSON schema definition. Following Web of Things provides a set of standardized technology building blocks that will help to simplify IoT application development. You can send data to SmartWorks IoT from a thing. To do this, you need to create a connection between SmartWorks IoT and the object to send the data. Data must be sent via HTTP or MQTT. If you want to connect via HTTP, the platform offers access through a REST API to all the resources. You can also send data using MQTT protocol. MQTT is the standard for IoT messaging. It allows for messaging between device to cloud and cloud to device. It follows a publish-subscribe pattern that decouples the client that sends a message, the publisher, from the client or clients that receive the messages, the subscribers. Client connections are always handled by a broker, which is responsible for receiving and filtering the messages, determining who is subscribed to each message and sending them. AnythingDB generates a unique set of HTTP and MQTT credentials for each motorcycle in the system, which allows the device to bidirectionally exchange data with SmartWorks. As you can see, this feature is really helpful to ease the process of provisioning the information of multiple motorcycles using the model defined before. Historical data sent to each motorbike can be found in the raw history section. As you can see, the incoming data from the different sensors of your motorbike is received here and then stored. Following the same process, you can add more collections to store different information. For example, you can have an orders collection to store the information of the different orders that you have made to require new types of parts. You can have another collection to store the inventory of all the parts that you have. And you can also store the information of the different users. Coming back to AnythingDB, let's see what other customizations we can make. From here, you can choose which columns to display. And you can also reorganize the order between them. I can filter, for example, to see the motorbikes with a battery level below a certain value. Filters can be easily removed from here. If you make an improvement on the version of your model, you may want to update all your motorbikes to that specific new version. For doing this, you can select all the motorbikes from here, click on Edit, and apply the new version to all of them. Now that we have our motorbikes database defined, we may want to define some business logic quickly. This can be easily done thanks to the Functions module that enables you to create and deploy custom code on the SmartWorks IoT platform without provisioning servers or building an API. You can write these business rules in Python, Go, and many other programming languages. When you select a programming language, Functions auto-populates the basic structure in the code editor. In this case, we are going to create a function in Python that generates a low battery event when the battery level falls below a selected threshold. Add the code and save to start the building process. Once it is completed, the status will have changed from pending to building and then to running. When the running process is completed, you can execute your function through HTTP or by linking it to an MQTT trigger or a cron trigger if you want to schedule its invocation. As we have to define an MQTT trigger to execute our function, we have two options. We can create a function referring to a specific thing, but if we want our function to be affecting multiple motorbikes, we will have first to create a label, so that we can assign this label to the different motorbikes that we will be monitoring. Using a label is the best option as they also have MQTT credentials. Labels can be found in the Space Settings section. To create a label, you just have to click on the new label, name it, and you can apply a color to them. This way you can have multiple labels and identify them easily. Once the label is created, we can move to the security pane. Here we can generate the credentials. If you want to create new labels for any other purpose, you can add them also from the AnythingDB section. If you haven't created your label, you can just type it here and click on Create Label. The label will also appear now at the Space Settings, and you can customize it from here. The topics to subscribe to the different motorbikes that we will be monitoring can be also found here. Let's copy it and use it as the event trigger on our function. In this case, we'll be specifying also that we want this function to be invoked whenever there is a change on the properties battery of anything inside the collection's motorbikes that is labeled with this specific label. Last thing we need to do is to define a trigger. Triggers are components that convert incoming messages to HTTP requests to asynchronously invoke all the functions that match certain criteria. From here we can create MQTT triggers but also cron triggers. To create an MQTT trigger, we need first to enter the host. In this case, username and password are the credentials from the label that we created before. The topic that we are adding is for listening to all the properties of all the things inside the collection's motorcycles that have assigned the label that we have created before. If you want to know what your trigger is listening to, you can also set up a callback URL. Let's test our function. First thing we need to do is to assign the label to the thing that we want to be monitoring. Let's try and change the battery value. By entering a low battery value, we might have received an event. Check here that the event was received with the data of the battery level. You can also check the message received at the callback URL. Remember, you can always come back to your function to make any changes needed. For example, you can add a Krogan expression, make any change on the code, and also test it from here. This way you will know if the logic applied is working as expected. You can also check the number of times your function has been invoked. Following the same structure, you can keep on adding more functions. For example, you can create another function to calculate the capacity, health, and kilometer, which are parameters of our motorcycle, based on the battery level. You can also create a function to calculate the health index, which is a parameter that measures how well the motorbike is performing based on the properties kilometer, health, and distance to empty. And finally, you can also create a function to update the state of your motorbike based on this health index. By now, your application is almost ready. Let's say you want to accelerate the development process by inviting your peers to the project space and begin collaborating in the shared space. At the same time, you will want to ensure that the users have the right level of access to the right entity in the platform. With the access control feature, you can create from general to fine-grained permission and set authorization rules for every piece of your IoT platform. In access control, from the users section, you can invite new users to join your space, but you have first to define a role to assign to them. Let's move to the roles section. The platform creates a default root role that can create, read, update, and delete any resource on the account. Let's create a collaborator role so your colleagues can act on your behalf on the platform. That way, users assigned to it can read and update the resources. However, they cannot create or delete the resources in the application. As you can see, you can easily add the policies for the different sections of our platform. Note that you can also change from allow to deny. You can also add custom policies from here. Just choose the section where you want the policy to be added and click on the resource type. From here, you will be able to check the subjects that you have assigned the role to. To add a new subject, click over here and enter the subject name. You can keep on adding as much subjects as you want to. Let's invite a new user using this new role. When a user receives an invitation, they appear in the Space Picker section. From here, the user can decide whether to reject or accept the invitation. When they accept it, they have joined the space and they can enter it. If you want to integrate with third-party applications, you can use apps and set the permissions needed for them. For this project, we have created an app to do the initial provision from a Python script. You can choose the scopes and get the credentials from here. Never forget to set up the policies. Now we are almost ready. The last thing that we need to do is to create our dashboard. Panopticon can be accessed from here in the real-time visualization section, clicking on the workbook section. Every user has its own root folder created where all the workbooks are stored. To create a new workbook, just name it and click on Create. First thing we need to do is to add a data table to fetch the data that we want to display. There are several global data tables available from here. We are going to choose the one for getting the historical data. You just have to enter your app credentials, the client ID, and the secret, and click on Generate Columns. See how all the properties available are displayed. Click on Refresh Preview to have a general overview of all the data available. Now let's go back to the dashboard. Draw a square with the size of the visualization that you want to draw. You can choose from a wide range of options. By drag and dropping, you can customize your visualization. In this case, I want to plot the battery levels of the different motorbikes, and I want the color to represent distance to empty. Color palette can also be customized. You can choose how to aggregate the data, how to order the data, and you can even add a title. You can also convert this file into a PDF to share your results. You can also easily access the data from here or zoom in to see in more detail. If you want to share your dashboard with your colleagues, you need to give permissions to them first. Give permissions by clicking on your folder, Permissions, and allowing the users that you want to. You can also choose how you want them to access your workbook. Finally, let's see a small real implementation to fully understand what SmartWorks is capable of and how to use it with the application that you are going to develop. Imagine you have an application like this one, and from here you are able to limit the speed of your motorbike to a certain value. Let's see how after setting the speed and clicking on the Set New Speed button, the property speed is updated with the new value on real time. This is also a good example to show another feature that the SmartWorks provides, which is the MQTT Inspector. MQTT Inspector allows you to track incoming messages to any of the entities that you have modeled. You can access the MQTT Inspector from the utility belt, clicking on the MQTT Inspector. A list of the messages and topics is shown, so you will know what topics are available. Expand the nodes of the topic tree to see specific details of the data. Whenever a new message is received, you can check the history values, last value, and even add more topics to be subscribed to. From here, we can also access function log. Logging enables you to know what is happening during the execution of a function. You just have to choose the function you want to inspect and make a change so that it can be invoked. Let's try with the low battery event. Whenever we enter a low value, we see that the post request was created successfully. If we enter a high value, and so the event is not triggered, we also get the message telling that no content was generated from this event. Functions log can also be accessed from the workers section, clicking on a function, and on this button. To end this small demo, let's try the last feature of our application, that was turning off the lights. Once we click on the button from turning on the lights, a progress bar appears until the action is completed. Once it is completed, we can switch to SmartWorks and see what happened on the application. Check how the action was received successfully. If you want to know more about the SmartWorks, you can always check our documentation. Here you will also find a tutorial about connecting your first device. Each of the sections in SmartWorks has also a link to its documentation section. Now that you have discovered how easy it is to configure product ecosystem, leveraging all the various tools provided in the SmartWorks IoT platform, I encourage you to visit us at swx.alterone.com to learn more and register for a free account to try all this by yourselves. Thank you for your time.
Thank you very much, Paloma. I should not, showing that I'm still muted. I should not be muted, I hope. And you can see the screen here. And I'm now checking the questions that came in. There are no actually questions here. Paloma, one question from my side. I mean, you explained as well how to access the platform. So is it true that everyone is invited to check it out and just to apply for a trial after that webinar?
Yeah, it's totally true. It's so easy. You just have to type the website. You don't have to download anything. So yeah, you just create an account and you can dive into the platform and see the different features. And if anyone has any question after doing that, then I'm happy to help.
Please try it out and check it here. As she said as well, inside of the SmartWorks IoT platform, you have as well Panopticon, the tool that Naman used standalone to display his race data. And you can easily as well bring in the workspaces created in the standalone into the Smart IoT platform. So try it out, check it, and let us know if there are some questions that occur. We, of course, will help you with that. All right. Any further requests from your side? It's getting a little bit silent here. But as I said, the recording of the whole session will be online soon, so you can check out as well later and contact us. But always, it's better to be directly in the call here, and we can interact. So if there is nothing popping up currently, I want to switch to the, thank you, Paloma.
Thank you, Armin.
Thanks. And switch here to the next presentation from Pritish. It is about all these different words that you hear. It's about data, deep learning, AI, machine learning, data science, data analytics. All these words need some, I would say, need some clarification as well for myself, who is a classical mechanical engineer. And Pritish will give a basic introduction to all that, and he will show in Knowledge Studio how we can, or you can set up as well, data analytics workflow easily and process data to achieve, a proper outcome of the data and to drive something. So Naman, he is assistant professor in mechanical engineer at the department at MIT University, Noida. And he is an associated with Altair since 2019 as an university ambassador. He is working with us. He created an ebook about artificial intelligence and machine learning, the data analytics of Altair. And he worked with us in several of the other webinars, specialized webinars in the past. And I'm really happy that he made it to present here. In addition, once again, about the machine learning and AI. So Pritish, he is in the call. I just check if he's in call, at least he will be available later on to answer your questions. Yes, I see him in the list here of the participants. So whatever you will want to ask him, go ahead and type it into the question form.
Hello and welcome everyone to this Altair's student webinar series. My name is Pritish Shubham. I will be presenting the details about the basics of data science and its application. The session will begin with some insight about the data and discussion on what is data science and what is managed inside the data science. It will be followed by a short discussion on machine learning and artificial intelligence. And thereafter, a brief understanding of machine learning process will be done. Towards the end, we will have a session on Knowledge Studio where we will see how a machine learning predictive model can be created by using Altair's Knowledge Studio software. So let us begin our journey of understanding data and its science. We have heard the term data a lot many times in our life, but never realized what actually is data and how it can be effectively used to accomplish tasks that appears impossible to be done by a human. A simple definition of data is, it is unprocessed raw input, which means any input which we get from any source can be termed as data. A more formal definition of data is, it is a collection of facts such as numbers, words, measurements, observations, or descriptions of things. This implies that starting from our school grade to customer feedback, or product price to product quality measures, anything can be called as data. Let us have some more real example of data. Now, many of us have seen F1 car sports numerous times. This sports deals with so many independent variables that is beyond human capability to see these interactions anymore. One such insight that we can see many times on our television screen is how a team is in lead and poised well to win. And suddenly a graphic comes up that says only 5% entire tire life is left, but still 10% of lap is remaining. Now there is no way to determine such a great detail of insight without the data. So how are these decisions, predictions being made? From where these data are generated? The answer is over 300 sensors are generating enormous amount of data every fraction of a second. These sensors are placed in 4 main units, that is around the engine, gearbox, power control module and data logger unit. All the gathered data are then processed to gain the insight and make predictions. A Google Map is one of the most widely used mobile app which seems indispensable from our life. Whenever we travel, we most often tend to use this app to know the best path to reach the destination and the least amount of time needed to do that. Now, how does a Google Map application decide which is the most suitable road to follow, live traffic situation, and how much time it will take to reach to destination? These tasks seems impossible to be done by any human being. So how does a Google Map know these details? The answer is again data. The data which is generated from us and many like us. Google Map gathers the data generated from users' mobile to determine the latitude and longitude and the speed of the car and use all these information to predict the live traffic situation and advise us the best path to follow. Similar example is related to the cab booking service portal. Through the portal, we instantly know how far is the cab, the estimated fare to reach destination dependent on travel time. So question is again, how does an online portal know such detail? An answer remains the same. The huge amount of data gathered from users' mobile and further processed to predict the outcome. There are many other numerous examples where we as a user play a significant role in generating data for companies and corporates. Facebook sees around 31 million messages exchanged every minute. YouTube have 500 videos uploaded every minute. Last year, billions of photos were shared online. So now you can realize that how everything around us is data. And what are we doing with such huge amount of data? Many corporates and institutions are using this in numerous ways. Some of these examples are already seen by us in earlier slides. Now question is, how do we use these data for leveraging its benefit? Here comes the data science into the picture. We use data science to get maximum benefit out of the gathered data. So now the next big question is, what is data science? A formal definition suggests that in the field of computer science, data science is a concept to unify statistics, data analysis, machine learning, and their related method in order to understand and analyze actual phenomena with data. This definition seems quite complex, so let us simplify the understanding. There are multiple domains in the field of computer science, which is coding, market research, and statistics. Every domain has its own features, and there is some area where these domains overlap. The subset of market research and programming creates a domain of data engineering. Statistics and market research forms the domain of data analysis. The most significant subset, which is formed by the overlapping zone of statistics and programming, is machine learning. This is the domain which is very trending recently due to its enormous potential in developing predictive analysis. We will discuss this in coming slide in detail. But looking further, another big aspect which came into the picture when all these three valuable subsets are overlapped to form a field of data science. So in simpler way, we can say that data science is the field which involves data engineering, data analysis, and machine learning. We can also say that data science or machine learning is helping to understand and analyze actual phenomena of real condition with data. Now, having understood that machine learning is pivotal in the field of data science, let us see more detail about machine learning. Machine learning term was first defined in the late years of 1950s by Arthur Samuel. According to his definition, machine learning is a field of science that gives computer the ability to learn without being explicitly programmed, which means without explicitly commanding the computer, called as machine, it can learn on its own based on the data. Machine learning is a data-driven approach which takes data as input and uses algorithm to determine the pattern of the data by correlating the independent variable with the target data, and as a result develops a predictive model which can be used for forecasting the future based on the past data. There are a variety of machine learning algorithms and each has its own significance and some limitations. Regression, classification, deep learning, and neural network are examples of some of the most widely used algorithms. Along with machine learning, there is another similar domain that is known as artificial intelligence. Many a time, these two terms are often confused. To have a clear distinction, we can see artificial intelligence as a bigger umbrella, which has ability to learn and reason similar to humans. Thereafter, machine learning can be seen as the subset of artificial intelligence. Machine learning process needs instruction in the form of program. However, it does not need to be explicitly programmed. Deep learning can be seen as further subset of machine learning, which uses artificial neural networks and learns from the vast amount of data. Having seen several details about data science, machine learning, artificial intelligence, and deep learning, let us move deeper and understand briefly the machine learning process. There are 7 different stages in the machine learning process, and most of them revolve around data. The process begins with data acquisition. In this process, information is gathered from a variety of sources. These can be in the form of numeric values as well as in the textual form. Data curation follows data acquisition, which involves cleaning up and correcting the raw data which was obtained in earlier stage. This stage involves data analysis, data cleaning, and data transformation. Altair's Monarch software is one such software that is best suited for the data curation process. Data exploration is the third stage of machine learning process. In this process, the clean data is further explored to check for the variance within it by the help of data analysis technique. In the fourth stage, machine learning model is created. In this process, the algorithms are developed which can process the curated data and formulate the mathematical equation that is best fit for the data set. Once the algorithm is created, data is then further bifurcated into training data and testing data. By considering the training data set, training of the machine learning model is performed in the fifth stage. In this process, the algorithm learns from the data and correlates the dependent and independent variable to determine the best fit model. Thereafter, in the sixth stage, model evaluation is done. Model evaluation is a method of checking the performance of the trained model. The testing dataset is used for the evaluation of the model. The final stage of machine learning is prediction stage. It is the process of forecasting the likelihood of the outcome through the trained algorithm on the historical dataset. All these 7 stages are followed whenever any predictive analysis is to be done on the gathered data by using machine learning process. Having said so many things about machine learning and its process, let us have some hands-on session where we can use a dataset for creating a predictive model. Altair's Knowledge Studio is the most advanced and user-friendly software which can create a machine learning predictive model with just few simple clicks. Altair Knowledge Studio is the data mining and predictive analytics software tool. Instead of writing numerous lines of codes, this software's graphical interface enables user to select the options from the list of menu and develop a robust machine learning model that can be implemented in a real-time condition. Knowledge Studio also enables advanced analytics to be built and deploy predictive models using repeatable workflow. The Knowledge Studio features include data preparation and profiling, variable selection, decision tree analysis, building predictive models, principal component analysis, market basket analysis, and many more. This image shows the graphical interface of Knowledge Studio software. It has multiple tools which can be selected from the menu bar. Towards the left extreme, we have Project Explorer, which shows list of all the projects that have been undertaken till now. The Workflow Process panel is the place from where various options are picked for the model creation. Now let us consider a real data obtained from the sensors of an electric motor and use Knowledge Studio for creating a machine learning predictive analysis. So the problem is to predict torque by considering various parameters of electric motor. The algorithm for this problem, which we will consider, is linear regression. 12 different variables are considered to correlate the target variable, which is motor torque. So let us now explore Altair's Knowledge Studio software. So this is Altair's Knowledge Studio platform, which we are going to use for creating the predictive analysis. Now to create a new project for machine learning, we have to select the option from the top of the menu by the help of left click of the mouse and give the name. For the time being, let us consider the name as Motor Torque Predictor. Once the project is created, you will see the blank canvas where all the activities can be performed. The first step into the Knowledge Studio canvas is to import the required data. The data which is generated by electrical motor sensor and compiled in a systematic form. To import data into the canvas, the steps to be followed are: from the workflow panel, inside the Connect tab, select File Import option and drag it into the canvas like this. Then double-click on this Import File node and define the path from where data need to be imported. It will take a few seconds to process the imported data. Once the process is completed successfully, you will see a green dot in the lower right corner of the node, and a new node of imported data will be created. You can also drag the node and relocate it to your desired alignment. You have to press on the node and drag it wherever you need that. After data import, the data exploration stage is followed. Now to do this, double-click on the imported data node and select the various options to explore the data. Inside the Data tab, you can also visualize the data which you have imported. It will only show first 100 rows by default. So if you want to see more, what you have to do is you have to press Show More, and then another set of 100 rows will be visible. For further data exploration, the statistical calculation on the imported data can also be performed. For this, you need to go inside the Overview report, then select Option from the above menu list and choose options such as Basic Measures, Central Tendencies, Measure of dispersals, etc., which you need for calculation, and then press Calculate All. So this will help you to explore the data and see what type of input you need to consider. Once the data is deemed fit, it is then bifurcated into two parts, which is the training dataset and testing dataset. Now to perform this bifurcation, go to the Manipulation tab, select Partition option and drag it into the canvas, and then connect the imported data to the partition node by dragging the arrow in this way. Once that has been done, double-click on the partition node and press Add. First partition will be named as Training Data. We can divide the data either by using a record count or by using % of total data. The latter is more preferred. So let us select the radio button of the % of total and then feed the value as 70%. In general, we consider 70:30 or 60:40 ratio for data partition. For this problem, we will be considering 70% of the data used for training of the machine learning model, and then 30% of the remaining data will be used for the testing process. After defining the training data, once again press the Add button and this time name the data as testing data and feed the value as 30% of the total, and then press Run button to execute the partition. Once partition is done, you will have two separate nodes. One is training data and other is testing data. Once again, drag the node to arrange them. We can also use Auto Arrange option to automatically arrange in the most suitable manner. This option can be selected from the top menu. After the partition, the model needs to be selected for creating the predictive analysis. This can be done by going into the Model tab and selecting the desired model. For our problem, we will be considering the linear regression model for the analysis. So we will drag the linear regression model into the canvas and connect with the training data. Now thereafter, double-click on the regression model and press Next. Then select the dependent variable as talk from the list. And also select the required independent variables from the list by either double-clicking on them or selecting all to get imported by the arrow button. Then press Run button to execute the model training. This process will take a few seconds to allow the model use the training data and correlate the dependent variable with the independent variables. Once the process is done, you will again see a green circle appear towards the lower right corner. This confirms that training has been successful. You can also double-click and check the performance of the model training. For the linear regression, the success of model is measured by the value of variance explained. The maximum will be 1 and least will be 0. The model training is considered to be the best if it shows the variance close to 1. For the problem which we have considered, we can see 99% variance is explained by the model, which is an exceptional result. Now, many more details can be further seen inside the output view command, such as currently selected sequence as well as the sequence. Inside the sequence tab, you can go down and see the formula which is used for predicting the talk based on other independent variable data. After satisfactory results are obtained from the model training, it is now the time to evaluate the model performance with the untrained data, which is the testing data set. Now to do that, we have to go inside the Evaluate tab and select Model Validation and drag it into the canvas. Once this model validation node is placed inside the canvas, we have to link this node with linear regression model and testing data set. Thereafter, double-click on the model validator and press Next twice and run the validator. The model validator will let us know how well a machine learning model is performing for predicting the unknown data. Now to check the model performance, double-click on the newly created testing node and go inside the Data tab. You have many options which is presented in the tabulated manner. You can see all the independent variables and dependent variables presented in the tabulated manner. In the same place, we can see the comparison of the result. Since our aim was to predict the talk, we have to go into the column of the talk prediction and see how well it is performed by checking the predicted values. The next to this column, we can also see the talk error column. This column shows how much variation is there in the prediction. The result shows marginal error is present in the prediction, which confirms model is performing very well. Once we found model performing satisfactorily, we can use this model to implement into the real system to use it further. The program can also be generated by using Action tab. So this is how we create machine learning predictive analysis by using Knowledge Studio. You can see how simple it is to create a predictive analysis by using Knowledge Studio software. And as I have mentioned earlier, it is very user-friendly and the graphical user interface help us to understand and visualize the whole flow of the machine learning process. So let us conclude our learning for this session. So we have understood that data science is a new technique that serves as umbrella to data creation, manipulation, predictive analysis and research. The data and capability to extract useful insight from data must be considered a key strategic asset. The gained insight from data can solve business and engineering problems. And in this digital age, It's very important to groom future engineers and managers to the data science technique. That's it from my side. Thank you for joining the session. And if you have any questions in your mind, I will be happy to answer them.
So I'm again sharing my screen, hopefully. Wait a second. Okay, so I thank you, Pritish, about the introduction, overview, and introduction of that really interesting topic here. I just learned that I have to unmute you and as well Naman, in that that's self-muted. I make you organizer. I think that makes it easier. And so panelists and organizers, now you're unmuted. I hope I can do the same with Naman as well. Are there any questions from the audience? I will check the question box here. Give me a second. Nothing came in. Pritish, if you are, can you just unmute yourself? Hey, thanks. Can you give me a short, I mean, only an idea of how you felt in working with Knowledge Studio here to build such a, I mean, a case, how long it takes for you to do that, and what you can, say, recommend to the students who want to explore that topic for their studies, but maybe as well for their teams competing in competitions. So that maybe what do you think, what you can recommend to doing them?
Right. My experience with this software, Knowledge Studio, is exceptional. Am I audible?
Yeah, but quite low noise, low. If you can speak up a little bit, that would be better.
Definitely.
Good.
So is that fine now? If this pitch is okay,
yeah,
should I answer this?
Good.
Okay. So what I mentioned is this Knowledge Studio experience for me is really exceptional, because before using this software, I did use other programming software where I need to specifically write several lines of code, maybe sometime 100 to 1,000 lines, to actually get that machine learning process initiated. And that too, every time I need to rewrite it again and again. And you can think of all those tedious time which it took me to actually get to the final result. But this Knowledge Studio is completely, you can say, user-friendly, and I feel this software can be considered by any of us, or you can say any person who want to create any type of predictive analysis, whether a student want to use this in their project, whether an industrial person who want to actually use some real case studies and then do those predictive work for the benefit of the own company. So everything is straightforward. In front of us, we can see, we can just have a few click on that and get the final result hardly within 5 to 7 minutes, which is definitely a big thing when we do coding with other software such as Python or R programming. So my understanding with Knowledge Studio is it's so simple that anyone can use, and I think most of us must use this software for our own benefit. So that was my experience.
Thanks, Pritish, and it's really encouraging for us, and I hope for you as well, listening to that webinar here, to try it out, to test it, make your own experience, and always come back to us and ask questions. Of course, watch the webinar, the recording of the webinar, if there are some things you want to know and to review. I just got a remark from Paloma that the last minute of her presentation was not shown. I cannot check directly here what was done in the past, so I have to rewatch the recording as well. But in the case I missed something, and that is what she said, it's pointing you to the learning material. I just want to play that last minute of her presentation to let you see where to go and where to find self-paced so training material. I will do that now directly from my screen, and I hope that audio is transmitted as well. So one of the organizer, or maybe in a question, please let me know that you can hear it or not. Maybe I have to reset a setting here. So that is the video she was presenting, and I think we stopped somehow at 32:20 roughly about the motorbike drive app here, and I will share it, include audio settings. How do I do that? Audio? Give me a second. I'm here. Share my screen window. That's what, oops, that is wrong here. Again, stop sharing. And going in video one, but I'm not sure how to add the video here. You can use option drop down and the presenter toolbar. Give me a second as well. Here, connect to audio. I'm not sure how to do that, but I will just play it and let me know if you can hear it. Okay, that gave you, now I stop this one here. I hope you could hear. I will later on see that in the recording because I don't get the feedback of the audio here at GoToMeetings. Anyway, I really thank you for attending today's webinar, and I hope you got inspired to use data for your projects, for your curriculum as well, by self-paced training or whatever, and explore all the possibilities with Design Explorer, for example, or give me a second here. Oops, that is on a and the Design Explorer, or with dashboarding using Panopticon, or doing an IoT application with SmartWorks IoT, which includes as well some dashboarding, and here at the end as well what Pratish explained, machine learning and Knowledge Studio. So you're welcome, invited to go on altauniversity.com, apply for a student license, or if you're a team as well, for team sponsorship, or talk to your faculty, to your professor, whether you have access to our software at the university. If not, reach out to us. We can talk about how to provide license to you in the best way. And let us stay in contact. Community.altair.com is as well a place where knowledge is exchanged, and I invite you to go to those forums, ask questions, answer questions if you know something that others would like to understand. So you are invited to do that. So thank you very much. In APAC and EMEA, where this webinar is meant to be or is targeted to because of the time slot during the day, it's live. And later the day, we will run the same session in the US time slot again. So if you want to attend that one as well, you can stay up a couple of hours and attend the US session. So thanks a lot, and let us stay in contact, and I wish you all a good day. Bye-bye.